Hello and welcome everybody. I've done my thesis about an I/O efficient shortest path algorithm for simple polygons. Shortest paths are calculated by thousands of PCs worldwide every day. Whether it's for GPS, for enemies in a video game that want to find the shortest paths in order to kill you faster, or for a Mars rover that has to navigate an entire planet. This is why shortest paths have been researched pretty much since the first PC was invented. But then what makes this algorithm special? Usually algorithms are bottlenecked by the CPU over here, by how many calculations it can perform, and it doesn't worry about how to get the data it needs to compute on. This data is usually loaded into main memory, the RAM over here, where the CPU can access it reasonably fast. Fast enough so that it doesn't become the bottleneck in an algorithm. The problem here is that we suspect it might become a bottleneck when the problem size grows so large that it doesn't fit entirely into the main memory anymore. Then the operating system has to start moving data around between the main memory, the RAM over here, and the hard drive over here. This would create a new bottleneck. As you can see, the RAM is connected directly on the motherboard, which is very close to the CPU. This is why getting data from the RAM is relatively fast. Getting data from the hard drive, which is all the way over here, the data has to travel through a lot of wires onto the motherboard and onto the CPU, which is a lot slower, almost a million times slower. This would cause it to stall your algorithm and become a bottleneck. So what did we do to solve this problem? We thought of a way to order and structure the data in memory in such a way that our algorithm can process it in a very efficient order, minimizing the amount of times it has to read data from the hard drive. In this thesis, we want to compare the performance of this new algorithm to an already existing one. So we have implemented a state-of-the-art algorithm that was designed around the CPU being the bottleneck. So it was optimized for use on the CPU, and this new algorithm that is designed around trying to minimize reads from the hard drive. So without further waiting, these are the results. On the x-axis, you can see the problem size. Our main memory has a size of 128 megabytes, so it's around here. On the y-axis, you can see the execution time of the algorithm in seconds. The red line is the state-of-the-art algorithm that was designed around the CPU being the bottleneck, and the blue line is the I/O efficient algorithm, so it's designed around reading as few as possible times from the hard drive. As you can clearly see, for larger problems greater than 70 megabytes, the I/O efficient algorithm is quite a bit faster. Then if we zoom in onto the smaller problems, you can see that between 10 and 60 megabytes, the internal memory that is optimized for CPU is actually faster. What this shows is that it's definitely worth the effort to think about how your algorithm gets its data. If it has to operate on very large problems, then it might be wise to try and think of ways to optimize your memory layout and how your algorithm access the data. Thank you for watching and have a great day.